Welcome, adventurers, to the Ultimate Explainer. Think of me as your guildmaster, and today we are opening up a legendary item, the Examiner's Playbook. We are embarking on an open-world exam quest straight through the official syllabus for Cambridge Mathematics 9709, specifically targeting the AS and A-level territory. Now, our main quest today is taking down a foundational dungeon boss of calculus. We are talking about integration as the absolute reverse of differentiation and the exact step-by-step game mechanics of integrating expressions in the specific form of open bracket ax plus b close bracket to the power of n. Whether you're an over-encumbered warrior just trying to survive the baseline marks, or you're a high-speed rogue hunting for that top-tier maximum yield loot drop, understanding the inner workings of this specific map is absolutely critical. We're going to treat your exam timer like a stamina bar, and every mark is crucial loot. Let's gear up and get into it.
Look at the screen right now. I want you to read this developer patch note straight from the source. The sheer weight of this statement is incredible, especially since it comes directly from a Cambridge Senior Examiner's report. Mastering integration is essential for success because this topic appears in every examination series. There's literally no way around it. You cannot hide from it. You cannot skip this zone, and you certainly cannot just wing it. This isn't just about memorizing a basic spell or a random formula. It is about grasping the underlying logic that the examiners are actively hunting for when they scan your paper. The stakes are extremely high. If you fail this, your overall grade takes a massive hit. But here's the good news. The roadmap to maximum marks is actually highly predictable once you know what to look for and how the game is coded.
So here is your quest log for today. First, we'll establish the core principles of integration. Second, we unlock the method mark strategy. Third, we scan for the top 3 examiner warnings. Fourth, we equip the deconstruct, solve, and evaluate framework. And finally, we'll secure your loot with a winning exam strategy.
Let's move right into Section 1, Core Principles of Integration, Building the Foundation. Now, the Cambridge syllabus makes it crystal clear. Top-performing students must exhibit a connected conceptual understanding. You can't just know how to clear one specific type of room. You need a conceptual grasp that is easily transferable to completely unfamiliar, high-level boss fights on exam day. And this perfectly illustrates where that conceptual grasp begins. Integration is the fundamental mathematical process that acts as the exact reverse of differentiation. It sounds super simple, right? But it is the absolute anchor for everything else. Imagine differentiation is you walking deep into a complex dungeon, taking specific turns, dropping down specific ledges. Integration is you perfectly reverse engineering those steps to find your way back to the entrance. If you lose sight of this exact reverse relationship, the complex algebra will quickly drain your stamina bar. So, when you are asked to integrate a composite function, like ax plus b all to the power of n, what are the actual mechanics? Well, since differentiating means you multiply by the power and then decrease the power by 1, reversing it means you do the exact opposite in the reverse order. You increase the power by 1, and then you divide the whole expression by that new power. But wait, what about the chain rule? When differentiating, you multiply by the derivative of the inside bracket, which is just a. So to reverse it for integration, you have to divide your whole expression by that a. Ground yourself in this definition. Every single time you start any integration problem, remind yourself, I am running the differentiation code backward.
So how are you actually tested on this out in the wild? The Cambridge Assessment Framework doesn't just want the final number. It demands logical, structured reasoning across 3 distinct cognitive domains. Think of these as your 3 core skill trees. First, you need knowledge and understanding of the fundamental formulas. This is your baseline stat. Second, you need application. This is your ability to put those formulas to work in standard, predictable combat encounters. But crucially, to get to the top band, you need analysis. The framework heavily prioritizes analytical depth. When you see a complex boundary condition or a nasty kinematics problem involving integrating velocity to find displacement, you are being tested on your ability to deeply analyze the scenario, not just execute a basic calculation. You have to read the command words perfectly. The difference between find and show that completely alters the requirements of the encounter.
Let's transition to Section 2, the method mark strategy, earning every point.
We are now moving from the theoretical map to tactical execution. I want you to picture 2 players in a co-op raid. We have player 1, let's call him Alex. He's our over-encumbered warrior. He writes down massive blocks of text, recopying the question multiple times, burning his stamina meter down to 0 on unnecessary descriptive definitions. But then we have player 2, Sam. Sam is our high-speed rogue. He dashes through the areas way too quickly, skipping mandatory puzzle requirements and jumping straight to the final answer in his head. Both players are going to fail this section. Why? Because of this incredible secret straight from the examiner's grading room. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. When you are integrating that ax plus b to the power of n, there are multiple mechanical steps. You are adjusting the power, you are dividing by the new power, you are dividing by the inner derivative a, and you are adding the constant of integration c. If Sam the Rogue tries to do all of that in his head to save time and makes one tiny arithmetic slip on the division step, he loses the entire loot drop. 0 marks. But if you show you're working, line by line, it acts as a non-negotiable insurance policy. It guarantees that the examiner can reward your mathematical logic and award you those precious method marks, even if your final number is slightly off. Do not try to speed run the math. Method marks are your save state.
Quest pause. Before we unlock this next top band layout to help you conquer your exam, make sure your guild feed is perfectly optimized. Take a second right now to subscribe to Ace the Exams and enable all notifications so you never miss our weekly strategic map drops, whether you are traversing IGCSE, O-levels, or AS and A-level territory. All right, let's look at the strict procedural conventions on screen. To lock in those method marks we just talked about, you have to play by the rules of the magic system. This means applying correct formats. Your integral signs must be clear. You absolutely must include the dx or dt notation to show exactly what variable you are integrating with respect to. It's not just decoration, it's mathematical grammar. You must use appropriate terminology and maintain clear annotation. If you are calculating a definite integral to find an area under a curve, annotate your upper and lower limits flawlessly on the bracket. And please, do not forget the plus c when dealing with indefinite integrals. That forgotten c is the most common trapdoor students fall through. Treat your exam paper as a professional, structured document. You are guiding the examiner, leaving a glowing trail straight to where your method marks should be awarded.
Moving to Section 3. Top 3 Examiner Warnings. Navigating the Traps. We are pulling data directly from principal examiner reports to uncover exactly where students get wiped out. This is the first major warning, and honestly, it's a fascinating one: confusing cause and effect. In the high-pressure environment of the exam room, students frequently lose marks by fundamentally confusing which operation causes which mathematical effect. You have the differentiation spell and the integration spell. For example, when differentiating, the effect is that the power drops by 1, and you multiply the whole thing by the original power and the inner derivative. But when integrating, the effect is that the power increases by 1, and you divide by the new power and inner derivative. Under exam pressure, the stamina bar is blinking red, students panic and they cast the wrong spell. They look at the inner coefficient a in our ax plus b term, and they multiply it instead of dividing it. They are doing calculus, but they are applying the effect of differentiation to an integration problem. You have to keep your cause and effect completely separated in your mind.
Welcome to the interactive viewer raid world. Here is the definitive list of the 3 most devastating mistakes from the principal examiner reports. Number 1, confusing cause and effect, which we just covered. Number 2, forgetting to check format and presentation conventions, like tragically forgetting that plus c constant of integration. And number 3, providing answers that are not specific to the given context. Let's do a live diagnostic check. I'm going to give you a scenario. A question asks you to find the exact equation of a curve that passes through the coordinate point 25 given its gradient function. A student integrates perfectly, gets an equation with a plus c at the end, and stops. Spot the defective item. Where did they fail? Exactly. They failed mistake number 3. They provided a general formula, not a specific answer. They didn't plug in the x value of 2 and the y value of 5 to actually solve for c. You must apply the specific context. To help you avoid this, I want you to equip a mental memory hack right now. Think CFC, cause, format, context. Write CFC at the top of your paper when you start an integration question. Have I confused the cause? Is my format perfect? Did I answer the specific context?
Here we go, Section 4. Deconstruct, solve, and evaluate. The cognitive framework. This right here is the systematic, repeatable combat combo that examiners expect to see when you tackle complex problem solving. Let's walk through how this builds an unbeatable strategy. Phase 1, deconstruct. Don't just rush into the math and start throwing numbers around. Identify the given information. Are you given a gradient function? Are you given boundaries on the x-axis? Break the question into logical steps. Phase 2, solve systematically. This is where you execute. Apply your integration rules precisely for that ax plus b to the power of n, showing every single line of working to capture those method marks we talked about earlier. No skipping steps. Phase 3, evaluate. This is the ultimate top-tier habit. Check your final output for reasonableness. Let's say you just spent 10 minutes calculating the physical area under a curve that sits entirely above the x-axis, and your final answer is -15.
Your evaluation step should immediately trigger massive alarm bells. A physical area above the axis cannot be negative. You probably swapped your upper and lower limits during the calculation. This DSC framework, deconstruct, solve, evaluate, prevents those fatal careless errors and ensures your mathematical reasoning is completely airtight before you move to the next room.
Almost at the victory screen, Section 5, a winning exam strategy, final review.
Let's synthesize the core theory, the methodology, and the trap warnings into a comprehensive, unbeatable plan. Part of a winning strategy at the AS&A level is the ability to evaluate mathematical models and evidence, which requires a robust comparative analysis protocol. Now, this might look like a humanities chart, but it applies directly to high-level math. When you're looking at different mathematical models or analyzing the limitations and assumptions made in a complex integration word problem, you need to be structured. Identify what's actually happening at your upper and lower limits, build logic using clear steps, justify your mathematical conclusions with evidence, meaning actually show the numerical substitution that proves why a specific point is a maximum or a minimum, or why a specific area is valid. And finally, synthesize your results to draw a firm conclusion that perfectly answers the original prompt. This level of rigor is exactly what separates a standard student from an outstanding Cambridge scholar. It shows deep, unshakable analytical maturity.
Expedition Successful Adventures, we've reached the victory screen. To wrap up this explainer, remember that mastering integration is all about structure. It's about decoding the question, pacing your stamina, showing every line of your working for method marks, and using your CFC checklist to avoid those common examiner trapdoors. Before you log off, make sure you permanently optimize your exam prep by subscribing to @AceTheExams right now. Hit that notification bell so you never miss our weekly Level Up Masterclasses. And drop a comment below sharing exactly which Cambridge subject and level, IGCS O, AS, or A level, you are preparing to conquer next. Thanks for running this quest with me, and I'll see you in the next explainer.